Infrared IR spectroscopy works because molecules are made of atoms connected by bonds that can stretch, bend, or twist like tiny springs. When IR light of the right energy hits a molecule, it can make one of these springs vibrate. The energy of the light is usually expressed as wave number nu in centimeters to the -1, which is just the number of wave cycles per centimeter, and is directly proportional to the photon energy E equals hc nu. Imagine a playground swing. If you push it at just the right rhythm, the swing's natural frequency, it goes higher. Similarly, each bond has a natural vibrational frequency. If the IR light matches that frequency, the bond absorbs the light and the molecule jumps to a higher vibrational state. The most common motions are stretching. Atoms move along the line of the bond, and bending. Atoms move perpendicular to the bond. The vibration must change the dipole moment of the molecule for the absorption to be IR active, just as a moving charge creates an electric field that can interact with the light wave. Each type of bond vibrates in a characteristic wave number range, much like a musical instrument has a specific pitch range. Chemists collect these ranges in a group frequency table that acts as a quick lookup chart. For example, a carbonyl C equals O stretch usually appears around 1,650 to 1,750 centimeters inverse. A hydroxyl O-H stretch shows a broad band near 3,200 to 3,600 centimeters inverse. And a nitrile C triple bond N gives a sharp peak near 2,210 to 2,260 centimeters inverse. These ranges are not exact. They shift depending on neighboring atoms, electron withdrawing or donating groups, and hydrogen bonding. Think of it as a recipe. A pinch of salt, the functional group, will always taste salty, but the exact intensity changes if you add pepper, adjacent groups. The tables help you match an observed peak to a likely functional group, providing the first clue in a molecular puzzle. The Beer-Lambert law connects the measured absorbance A to how much of a substance is present. A equals epsilon Cl. Here, epsilon is the molar absorptivity in liters per mole per centimeter, C is the concentration in moles per liter, and L is the path length of the IR cell, usually 0.1 to 1.0 centimeters. In IR, you often work with thin film or neat samples, so L may be the thickness of a KBr pellet. By measuring A at a known concentration and thickness, you can solve for epsilon, which tells you how strongly a particular vibration absorbs light. For quantitative work, you plot A versus C, a calibration curve. The slope equals epsilon. This allows you to determine unknown concentrations in mixtures, much like using a ruler to measure a shadow's length to infer the object's height. The most frequently encountered functional groups each have a signature IR pattern. C equals O carbonyl, strong, sharp stretch near 1,700 centimeters inverse. Ketones appear around 1,715 centimeters inverse, while acids shift lower about 1,710 centimeters inverse because of hydrogen bonding. O-H hydroxyl, a very broad, often rounded band from 3,200 to 3,600 centimeters inverse. Free alcohols give a sharp tip near 3,600 centimeters inverse, whereas hydrogen bonded, for example in water or acids, broaden it and shift it lower. N-H, primary amines show two sharp peaks near 3,300 and 3,400 centimeters inverse, symmetric and asymmetric stretches. Secondary amines give one broad peak near 3,400 centimeters inverse. C-N nitrile, a narrow, intense line around 2,240 centimeters inverse. C-H, aliphatic sp3C-H stretches appear just below 3,000 centimeters inverse, 2,850 to 2,960 centimeters inverse. Aromatic C-H stretches are a bit higher, 3,030 centimeters inverse. The pattern of multiple peaks can tell you about substitution, for example methyl versus methylene. By matching observed peaks to these templates, you can sketch a likely functional group skeleton of the molecule. Real molecules often have many vibrations that crowd together, creating overlapping or combination bands. Imagine several singers hitting notes that are very close. You hear a blended chord rather than individual voices. In infrared, overlapping occurs when two different groups absorb in the same region. For example, CH bends around 1,450 centimeters inverse, can overlap with CH2 scissors. Combination bands arise when two fundamental vibrations are excited simultaneously, giving a peak at the sum or difference of their wave numbers. For complex molecules, you use deconvolution techniques like Fourier self-deconvolution, or compare to reference spectra of fragments to tease apart the contributions. Knowing the typical full width at half height FWHM of a band helps. Broad bands often signal hydrogen bonding, while sharp bands suggest isolated functional groups. Explanation: whether a vibration appears in an IR spectrum depends on molecular symmetry. Group theory provides a systematic way to decide this. First, assign the molecule to a point group, for example C2V-D3H based on symmetry elements, axes, planes, centers. Then, use the character table for that point group to find which vibrational motions transform like the x, y, or z Cartesian coordinates. These are IR active because they change the dipole moment. For example, carbon dioxide linear d infinity H has a symmetric stretch that does not change dipole moment, IR inactive, but an asymmetric stretch that does, IR active. The process is akin to sorting dance moves. Only those that involve a hand waving change dipole are seen by the audience IR detector. By counting the irreducible representations that match the dipole coordinates, you predict the number of IR bands and can assign them to specific motions. Typical exam questions ask you to draw the structure from a given IR spectrum, B. Assign peaks to functional groups, or C. Perform Beer-Lambert calculations. An example: a 0.250 centimeters KBr pellet shows an absorbance of 0.750 at 1,715 centimeters inverse for a ketone. If the molar absorptivity epsilon for a typical carbonyl stretch is 150 liters mole per second centimeters inverse, calculate the concentration. Using A equals epsilon CL, we solve C equals A divided by epsilon L equals 0.750 divided by 150 times 0.250 equals 0.200 moles per liter. Another common task is to identify overlapping peaks. Given a spectrum with a broad band at 3,400 centimeters inverse and a sharp peak at 2,240 centimeters inverse, state the likely functional groups OH hydrogen bonded alcohol and nitrile. Practice interpreting these patterns builds intuition for quick identification. Errors can creep in at many stages. Baseline drift occurs when the detector signal slowly changes, giving a sloping background that masks weak bands. You correct it by subtracting a smooth baseline. Instrumental resolution, typically 4 centimeters inverse for a FTR, limits how close two peaks can be before they merge. Particle size in KBr pellets or film thickness can cause scattering, leading to artificial broadening or intensity loss. Atmospheric carbon dioxide and water absorb strongly near 2,350 and 3,400 centimeters inverse, so you must purge the spectrometer with dry air or nitrogen. Finally, sample preparation. Overpressing a pellet can introduce stress-induced shifts. Awareness of these sources helps you produce clean, reliable spectra. IR spectroscopy tells you what bonds are present, but it does not reveal how atoms are connected. Combining IR with nuclear magnetic resonance, NMR, and mass spectrometry, MS, gives a full picture. For instance, IR may show a carbonyl stretch, approximately 1,700 inverse centimeters. NMR can tell you whether the carbonyl is part of an aldehyde characteristic proton at 9 to 10 parts per million, or a ketone, no aldehydic proton. MS provides the molecular weight and fragmentation pattern, confirming the number of carbons and heteroatoms. By cross-checking, if MS shows a loss of 18 atomic mass units, water and IR shows a broad OH band, you can infer a carboxylic acid. The triangulation of data reduces ambiguity and leads to confident structural assignments.